Hi, I'm Wallaber, the developer of Replicube, the game that takes Picross 3D and the joy of shader coding and combines them into a nerdy but chill puzzle game. The game's pretty simple. You are given an object like this, and you need to recreate it by writing code. Your code will produce a 3D object, and you need to match the target object. So you can see here I've got a little bit of code, and we need to update it to match this object. So we could say, oh, what about this? Okay, there we go. But the problem is we need it to be not so thick. There we go. I've had some requests from players for me to make some kind of tutorial series or something about some of the topics and techniques that are involved in this game, but also apply to coding and graphics programming in general. And the game now has a Puzzles of the Week feature, so I think I might try a little series here where I just talk through solving the current puzzle of the week, and I won't post it until that puzzle has already been archived so that it won't spoil anything for people who want to play along. So the current puzzle of the week is actually a hard puzzle. It's this one right here that's like a sort of fountain with this interesting roof over it. So let's just sort of talk through how we might go about solving this puzzle. As you can see, we are given some starting code, so we actually don't need to solve the pattern for the grass on the ground. And you can also use this little show comparison button here, and you can see here anything red means the voxels don't match at all. So there's a voxel missing where there should be one, or I have a voxel somewhere that shouldn't be there. Yellow means the voxel is in the right place, but it's the wrong color. And green means perfect match. The voxel's in the right place and it's the right color. So we can definitely see here that the ground has already been provided for us. So I think we're going to start with this interesting roof. And if we look at it from the sides, it definitely looks like some kind of a circular shape, kind of like a tube, two tubes. That's just the top half of those tubes, and they're intersecting. So anytime we have a circular thing involved, we're going to end up using the Pythagorean theorem. But basically, the reason we're using that is because we want to know distance. We want to know if there was a circle going in this direction here on this puzzle. Is a particular point, a voxel, inside the circle, outside the circle, right on the circle? And so in order to figure that out, for a circle, it's distance, right? Distance from the center of the circle tells you, like, that's how you decide if you're inside a circle, outside a circle, on the circle, is based on distance from the center point, right? And when you have a 2D grid, if you want to know a distance, you can use the Pythagorean theorem. A squared plus b squared equals c squared, right? So a squared plus b squared equals c squared. And this would be something like this, right? You have a triangle that looks like this. Right? You get it. You're seeing this come together, right? Wow, maybe we could do a few more typos, right? Okay, so here's our like triangle, okay? And like maybe it finally connects right here. Okay, in this scenario here, this is A, over here is B, and this diagonal line is C, right? That's what the Pythagorean theorem tells you. It's like if you want to consider the relationship between the right triangle and the hypotenuse, it's A squared plus B squared equals C squared. Okay, well, this length here would be the distance to any particular voxel, right? So, you know, right over here, that is go over 8, go up 3. Or actually, we're looking at the wrong one. Let's look at it this way. So we have x and y. So right here, this one is go over 6, go up 5. This one is go over 3, go up 7. Those are our A and B. And so what we want to know then is, well, what's the distance from this origin to those spots? because that would be C, and that's the thing we care about. If that number's big, we might be outside the circle we care about. If that number is small, we might be inside the circle we care about. If that number's just right, we might be on the circle we care about. Okay, so that means A in this case is actually X. So let's swap that out. And B is actually Y. So we'll swap that out. And C is still like this number we care about. So let's flip this around and put it at the beginning. It's starting to look a little bit more like code now. Okay. But let's have this like squared thing. So if we want to get rid of squaring, we can do the opposite of squaring, which is square root. So we get rid of that over here, and we put this whole thing inside square root. Okay, so now we actually have this variable we just created. This is like valid code now. Make a variable called C and set it to the result of x squared plus y squared, all square rooted. Okay, so let's try something here. Let's just temporarily comment out this code, and let's just say return C and see what we get. And you can right away see that we're definitely making some kind of circular pattern. Now, let's just talk for a second about what are we actually seeing here. And this is a super common thing that you would want to do in Replicube, but also very frequently you want to do in shaders. Shaders, the result of the shader is colors on the screen, right? It's not like a normal program where you might produce some output in the log or in a file or something. And so how do you debug a shader? Like if something's wrong with it, how do you tell what's going on? How do you check your intermediate steps are doing what you think they are? A common technique is to actually output values as a color. And that's what we're doing here. So you can see actually, look, these colors down here, white, gray, black, they are the numbers 1, 2, 3, 4, 5, 6, 7, 8, up to 16. And so here we can actually see this distance on the grid here. In the center here, the distance was basically 0. For all these voxels, the distance was basically 1. I'm saying basically, and I'll explain why in a second. And all these, you can see that the color is 2, which means the value, this distance was a 2. And then here's where it was a 3. Here's where it was a 4, 5, 6, 7, 8, 9, etc. All the way in the corner here was 11. Now, I said kind of the distance. Why is that? Well, that's because when you do this, this number here is not going to be nice round numbers, right? If you go over 1, up 1. What's that mean? You take 1 squared, that's 1, plus 1 squared, that's 1. Add them together, you get 2. Take the square root of 2. The square root of 2 is not like a nice round number. It's not a 1 or a 2 or a 3. It's like 1 point blah, 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 blah. So C is a decimal number. And what happens then is Replicube says, well, if you return a decimal number, there's no such thing as a decimal color in our palette down here. So we will just throw away the decimal part and keep the whole number part. So for example, square root of 2 is 1 point blah, blah, blah. When we try to turn that into a color, we just throw away the blah, 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 and we're just left with a 1. And so it's a little bit like rounding down. Like if the number was, you could actually describe this region right here. See where everything turned gray? That's a 2. So for these voxels to have resulted in the value 2, the color gray, the distance, this C value that we're calculating here, must have been anywhere from 2.0 to 2.99999999999. And then all of these here would be everywhere where that C value was from 3.0 to 3.9999999. Okay? And we can see that pretty quickly if we try to isolate a specific ring on this circle, right? So like let's say, let's just try and make a tube that's right at this purple distance, which is 6. So what if I say return C equals 6? And you can see right away, like what happened to our beautiful circle? The beautiful circle is gone. And that's because now we're no longer saying, hey, take this number, throw away the decimals. We're saying, no, take this specific decimal number and tell me, is it exactly 6? And you can see that it was only exactly 6 where the numbers worked out perfectly, right? When you're on the, axes, where over here is literally go over 6 and no up or down 0. So that math would work out to 6 squared plus nothing, then square rooted. You're right back to 6 again. So you land on exactly 6 here, but all these intermediate ones, they actually weren't 6, right? There was some weird number that was somewhere between 6 and 6.99999. So the way we can fix this, there's a lot of different ways you can do it, but we can kind of say like, well, if I want to say, hey, throw away the decimal, I can say that by saying, give me the floor of C. Floor says, keep the integer part, throw away the decimal part. By the way, which is kind of like rounding down. There's also ceil, which is short for ceiling, which is the opposite, which is round up. So if you have 2.1, consider it a 3. If you have 2.8, consider it a 3. So that goes upwards. And you can see that it's a little different here. Now these ones over here popped up one because they were 6 or higher, so they rounded up. And there's also round, which would do normal rounding you might be used to, which is like if it's less than 0.5, go down. If it's 0.5 and above, go up. And so there's different ways that you can sort of basically take your decimal messy number, this distance in this case, and turn it into discrete whole numbers that make more sense in a grid like we have here. Okay, so let's go back and look now. And we think it kind of looks like we wanted it to go all the way to the edge here, right? So let's go back and look at this. Okay, so what were the ones that go right to the edge? And actually, now that I'm looking at it though, it goes over 3 and then starts to go down. And if we look here at the edge here, that's too many. So it's probably maybe rounding. There we go. Look, over 3. Now if you look at these orange values, they look a lot like the edges of this here. Boom, boom. Then there's like a little corner piece like this, and then this. Okay, so that number looks good. That number is probably 8. Boom. Okay, let's quickly take a look. Let's compare. Yeah, look. So see this bit here? This is correct. Okay, so we figured it out. We have the top of this thing, but okay, we only need the top half of this like tube. So what we could do is we could change this. We'll say if this thing is 8, then we're gonna return white. Let's say. Okay, everything looks the same, but now we could add in a condition. We could say and y is greater than or equal to 0. So we only want the top half. Okay, that looks pretty good, right? And then now we need to get this other one, the one going this way, because there's 2 of them, and it's actually like this weird intersection of them, right? It's like the combination of those 2 things. So let's call this C1 now. Okay, there we go. And let's make a C2, which is going to be the square root. But in this case, when we look at it this way, now our coordinates involve z and y. So it's going to be like exactly the same thing as this, except I swap out z. Okay, so now if I say C2, we have a tube going this way. And if I say C1, we have a tube going this way. Okay. Now, what we want, though, is like, you see, what if I did an or? So what if it's this or this? And we're going to get kind of an interesting result. Oh, also, this is actually a common thing. You're like, what is going on here? And this is like, look, we're combining or and. And that's a little tricky. It's like, how does this resolve? What this turns into is like, if this is true, or all of this is true. And so you can see like, if we temporarily get rid of this, we get that one. And that's why here you see that whole circle. And if we get rid of this, you see just the top half of this one. So combining or and is a little tricky. Sometimes you need to add parentheses to make things more clear. Or what I might do in this case, I don't mind just adding a little more code to make things clear. So I'm just going to grab this thing and say, look, this bit is a condition over the whole thing. So we'll go like this, and we'll just put this inside here. Okay, so now we just can't go below 0, right? But yeah, if you look at an or is not what we want. Look, or is like, it's like allowing both, right? And that's not quite what we want. Let's try and. And's a little different too. That's only the voxels they have in common, which isn't quite what we want, right? If we go look at this thing, it's like we need the shells of both of them, but only where they are. It's like we took two tubes and we fused them together. So let's think about how we might be able to make that effect. It's not and, it's not or. So it's going to be something different. One thing we could do is we could go look at it and say like, okay, well, like let's say, you know, we are at like this voxel right here. You know, like we want to only be, if you look at it from this point of view, actually, if you look at this like 45-degree angle, right? If you cut this like this, then anytime we're in this quadrant up here, we want the tube going up and down. And anytime we're in the quadrant down here, we want the tube going up and down. But when we're over here and when we're over here, we want the one going the other way. So that's the condition. It's like when we flip to the different quadrants. Okay. So let's think about that. How would we like isolate those quadrants? So let's do something like this. Let's say return x is greater than z. Whoops. And let's comment out this code here for a second. Okay, let me go look. Okay, so that's like a diagonal. What if we do absolute value of x? Okay. We kind of want the empty space there. Like that. And if we put abs z in here, okay, there we go. So now we have like two regions here, you can see, right? The region where this is true is the up and down region. And the region where this is false is the empty space right now, right? Because when you return a Boolean, true becomes filled in, false becomes empty. So again, I'm just like outputting these results and then looking at them visually to see what we're doing. So this kind of looks like what we want to do. So what we could do here then is we could say, okay, we have this condition we care about here. So now let's go back here like this. And actually what we want is a high level thing that says, if this is true, then do something with this stuff, right? Else do something else. Okay, so then let's try this. Okay, so look, now, right, if y is greater than or equal to 0, so we're only in the upper portion of the entire space, and then if x is bigger than z, so this is all the places where the x values are bigger than the z values, ignoring positive and negative, right? So like right here, you can see, or sorry, x is less than the z, excuse me. So here you can see like x equals 4, the red number, and z is -6, so 6. 4 is less than 6, so this is the spot where the x is less than the z. And then we are picking which tube to return here. See, if I change this to a C2, we would return the sides of the other one, right? Which was not what we want, right? We want this. So then in theory, I can just put this down here and say, okay, else, so when we're in the other space, return C2. And look at that. Now we're getting somewhere. Let's test our little comparison here. Look at that. We made the roof. Looks quite nice. And so now I can go back down here and I can uncomment this out. And we have got a lot of this coming together. Okay, so let's try and get these poles here. Though the poles are pretty simple, right? Because the poles are just at the edges, and the thing they all have in common, if you look, this one's at 8, -8, this one's at -8, 8, this one's at 8, 8, and this one's at -8, -8. So it's where all x and z are matching if you forget plus or minus, right? So we could do a thing down here. Let's actually do this. Let's call this the roof. And then let's do the poles. Okay, so if x equals z, then, and just sometimes we've got a lot of colors going on. I'm going to pick a color we haven't used yet so we can isolate and see the specific conditions we're working on right now. So let me just say return red and let's see what happens. Okay, so we got like, that's everywhere that x equals z. And that kind of makes sense. It's like a stair step because these are all the spots where the numbers match, right? -7, -6, -5, blah, blah, blah. Okay. But we actually only cared about when they're at the edge, which is 8. So we could say and x equals 8. Okay, so we got one side there. Now, we're too tall, but I had a thing here which is like if y is greater than. So I could change this to be an else, put all this inside that, and then do this. And now we are only able to affect these voxels here. Okay, now we're going to have a problem where we're overwriting the ground, you can see. So we can solve that a variety of different ways. But let's come back to that. Let's get the rest of our poles. So if I put an abs around the x, now x plus or minus will match. And I put an abs around the z, plus or minus will match. There we go. Oh, and now the problem is we are only looking for when x is 8, so we're only going to get the positive side. So I got to put an abs around this as well. And now we've got all 4 poles. Okay, so we can probably switch this to say return white now, because that's the color in the reference. Okay. And yeah, now we have an order of operations issue, which is that because we return white here, down here, the code that would return green for the ground never happens for these corner pixels because we've already said, we're done, get out of here, white, move on. And so we don't want that to happen. So there's a couple of different ways we could fix this. If I just move this code up, by the way, if you highlight one or more lines and hold down Alt and then press up and down, you can just slide code up and down. We could just like go all the way up here and put this code at the top. And now you'll see that those take the priority, and maybe too much priority, because look, now the poles are being interrupted by the grass. So we could change this. What if we leave the ground its own thing and make, so this is the ground. And this is the grass. Okay, so now I could grab the grass and say, you go after this stuff. There we go. So we let the ground take priority, the green. Then we do the roof. Then we do the poles. Then we do the grass. Okay, so we're like almost there. Now we just have to do this fountain. And look, we got more circles involved. We definitely got more circles involved here. So let's take a look. Okay, so there's this like gray color. It's like a circle. Then it gets thinner. Then it's a pole. Then it's a circle, circle, circle to the ground. Okay, so let's just try and like figure this out. Okay, so let's go down here. And let's say this is the fountain. Okay, so this time the circle involved is this way. So this is going to be X and Z. Okay, so we could say like, let's call it FD for fountain distance equals square root of X squared plus Z squared. Okay, and so here we could just say return FD, and C is probably going to be mad at me for having this code down below the return statement. There we go. So if we look now, we still have our ground, but then here's our distance. And we can see this looks pretty close. What is this? At 4, which is 4 is right here. But this thing's like thicker. Look, it's like, and here we're just like skipping. Like if I say at the equals 4, equals 4, we're going to get that problem where everything disappears. So then we got to decide what operation are we using to turn the decimals into whole numbers. So we could say round. Okay, that looks right actually, right? That looks right. So it looks like we want to round this. I'm going to go ahead and put this up here. Okay, so now we don't need to do it twice. And do that. Okay, so there's supposed to be like that. There's 3 of them, but then there's also this center piece, right? And then it gets a little wider there, a little wider there. And I'm not worrying about the water yet. Okay, so it would be cool if somehow we could sort of make all this. Let's do this. We'll say the outer ring. Okay, so that's if what? If y we want it to stop right this is the highest level right here. So that's where y is -5. So if we could say y is less than or equal to -5, then if f equals 4, then return gray. Okay, let's see what we got. Boom, we've got the outer part. So now let's make the inner part that looks like the actual part that like spills over here. And you can see basically what happens is there's just a single, let's look at it like this. There's just single dot of gray, dot of gray, dot of gray, dot of gray, dot, dot, goes a little bigger, goes a little bigger, and it stops. Okay, so basically the radius is tiny and then it gets bigger and bigger. Okay, so let's look at this top spot right here. Where is this? This is y equals -1. So we could say if y is less than or equal to -1, then if fd equals, what do we think this is? 2, maybe? Then return gray. Okay, let's see what we did. So there we have a new tube that goes a little taller, and it's, I think it matches at the top. Let's take a look. Yeah, see the green there? So that looks pretty good. Okay, so now our problem is we need it to become smaller here, and then just here, all the way down to a single dot. And so you can think about this and be like, okay, well, I could just do a million if statements, right? Like I could say if y equals -1, and all we get is this top ring. And then I could say, you know, maybe else if y equals -2 and fd equals 1, then return gray. And okay, now we'll get the ring below. See, we went down 1 and we said we care about when it's a little bit closer. And then we could say else if y is, you know, less equals -3 and fd equals 0, then return gray. And okay, now we got the dot there, but we need the dots to go all the way down. So you could be like, okay, I could make a bunch of those, or I could realize maybe I just say less than or equal to -3, and then we get that. So that works. We could move on, you know. But this feels like something. If you look at this pattern, look. If you look at these 3 statements here, it's just like this is changing by 1, and this is changing by 1. So there's got to be a way that we could like combine that. And there is. Basically, what we can realize is that we can take y into account over here, because the y values are changing by 1 as we go. So it's kind of like we could involve the y. So let's try it. Let's go back to this. Okay. And let's get rid of the y conditional, or we'll say if we're less than, oh no, we already have that up here. We'll get rid of the y condition altogether. Now we're back to our tube. And then let's just say like, okay, well, what if it's 2 plus y? And actually, look, that's really close. Look, it looks like at this spot here, we ended up with a 1. So that means like it was a 2, but then y was a -1, so 2 minus 1 is 1. And then we ended up with a 0 here, and then it disappears, so that probably means we went into negative numbers. So what if we said, just as a test, 2 minus y? Okay, that's the opposite. Look, now it's getting bigger as it goes down. Okay, so plus y was good, but we were like, we wanted to be a little bit bigger, so we could just say, what if it was 3 plus y? And now look at that, we're super close. It's like when we evaluate it where y is -1, we get a 2. That makes sense, right? 3 plus -1 is 2. And then when y is -2, 3 plus -2 is 1. And so the size of this is 1. And then it becomes a 0. And then it would become a negative number. So we don't want to go negative. So what we can do is we can say, take this thing and say, do this calculation, but don't let it go below 0. In other words, give me whichever one is bigger, the maximum between this and 0. And now you can see, look at that. Anytime that calculation would have gone negative, it says, well, 0 is bigger than negative, so I'll give you your 0 back. And so now what we have here is something that will always be 0 or bigger. 0 or bigger. If this result is bigger than 0, we'll take it. Otherwise, we'll take 0. So you can see that max is almost like an if statement. It's almost like saying, look, I got these two things, you know, and if this one is, if this calculation is, in this case, less than 0, then do one thing, else do the other thing, right? But you can kind of just like put that all in here so we can do all this in one little calculation. So that's pretty cool. Okay, so there we go. We're super close now. We just need the water. So let's put the water up above. Yeah, so this is the outer ring plus the inner structure. Okay, so let's do the water. Okay, so let's look at the water. The water is what? It's color 14, which is light blue. Okay, so we're going to do something to return light blue. So we're going to say if y, and if we look here, you know, this one is down here at -6. So we could say y is less than or equal to -6. Then return light blue. Okay, and now of course that's going to be like, well, now we're just in the ocean. Okay, let's bring back everything. Right, so we want to not only have the water be that high, but only be inside this bit here. So that should be, and the fountain distance is less than 5. Oh, now you know what? Oh no, it was 4. It's 4. But we have like a weird thing here where now, because this is coming first, our water is going to take over. So if we go look inside here, like let's look like this. Look, right here, the water is taking over instead of letting this pillar come through, right? And if we go look at the real one, the pillar goes through. So we got to adjust the order of this. We could put this after all this, right here, right? And so now we know, we can let this come back in now as well. Okay, so there we go. We got the water filling right there. Now we're almost done. Look, if we do a show comparison, we're 99.39% done. All we need is the water spilling over in these columns and filling the top of the thing. And let's take a look real quick here from a side view like this. So we need the dot of water here and the bit here and then filling over. Okay, so that part we might be able to do here. So you can see, what are we doing here? We say like, okay, if you're less than -5, then we do that thing, blah, blah, blah. Here's the part that is this pillar, right? And right now we're saying if this is exactly equal to this, make it gray. But what if we said, and if it's less, do something else? So let's grab this and we'll make it into a little variable. We'll say target distance. All of a sudden I'm making a long variable name. I don't know. So then we can just put this in like this. No changes. We're back to where we were, right? But then what if we do an else here? Else, return red. What does that do? Look, that helps you see what's going on here. Here we're saying if we're less than -1 in the y, less than or equal to -1 in the y, and then if this particular thing is true, do gray. But here are all the other voxels that are being tested. And so right now it's like, well, they weren't exactly equal, so whatever. And what we have here is we have the area where we want to put the water and then the area where we don't need the water. So here we could say else if FD is less than target distance, then. And now look at that. We found the voxels where the distance to our little circle was smaller, right? And so that can be that. So now we have one last little bit, which is we need the water that's spilling over, which the water that's spilling over is actually really similar to these columns, right? So I'm going to go up here and just say, let's call this the spilling water, okay? So how did I do the columns? They were right here. It looks something like this. Let's copy that down, okay? And let's look what that did. Okay, let's change this to, you know, yellow. Okay, so we've got our columns back, but they're extending to the top now because we don't have any additional checks. So where does this actually need to be? It needs to be at a distance of 2. Oh, right, but these are at the corners, and we don't want the corners anymore. We want the centers. So that's a little bit different. That would be like a different pattern where we want basically just one number to be big, right? We don't want x and z to match, actually. We want x to be a number and z to be 0, or z to be a number and x to be 0. But we can actually do that with a different thing here. Watch this. If I say, just as a test, let's say if true, then, okay, so now we just get tons of yellow. What if I return x plus z? So we get like a diagonal pattern. If I do the absolute value of x, it's going to flip across the x-axis. And if I do absolute value of z, it's going to mirror across the z-axis. And now we get, like if you look down here, we get this kind of cool diamond pattern. And this is actually kind of what we want. Maybe not. No, it's not. Right, because we only want these 4 values right here. Okay, so maybe what we'll do instead, we'll say, let's see, the water goes from -1 in the y to -5. So we could say in range y, -5, -1, then, okay. In range, there we go. So we've limited this check to just right there, okay. And then we could say, okay, if x equals 0 and absolute z equals 2, then return light blue. Oh my god, look at that. We got water pouring down. And then we can just say, well, okay, it's that, or z equals 0 and abs x equals 2. We did it. Okay, so take a look at my code here, okay? And then later, if you go look at this code compared to the top solutions on the leaderboard, you will see that there is an infinite number of ways to make this more efficient with way less code or way less cycles. But hopefully, talking it through like this, you can get a feeling for kind of like how you can sort of take a problem like this, break it up into smaller pieces, and then debug it and visualize it as you go. And those are all techniques that I think really make a lot of sense. So I'll be back in the future with another video for the next puzzle of the week. And if people like this series, then I'll keep making them. Anyway, thanks for hanging out today. Talk to you later. Bye.